All right, hello linear algebra students. This is week 4, and we are talking about coordinate systems. It's the next natural step after learning bases, which is what we learned last time. If you have a basis, you can represent any vector in terms of that basis, which gives you a coordinate system. So let's go ahead and look at this first one here, first theorem. I'm going to move pretty quick because we're going to try to cover 2 sections in about 45 minutes, which is a lot. So let's just get to work. So if you've got a basis, B1 through Bn, which it's for some vector space V, then you can represent every vector x inside the space as a unique set or a unique combination of those basis vectors. So here we're writing x as a sum of the basis vectors, a linear combination of those basis vectors. Now, the next definition is in that scenario, when you have x represented in terms of those basis vectors, you can use those weights to create a real vector. So this is now a real vector inside of Rn, and it's just the weights. So this is called the b coordinates of x. Now we've turned this abstract vector x, which could represent a polynomial, it could represent arrows, it could represent something less concrete than a real vector. And so what we're doing is we're converting that abstract vector into concrete weights inside the real vector system. These are called the b coordinates of x. It's just converting to real vectors is all you're doing. The b coordinates of x mapping from x to its b coordinates is called the coordinate mapping determined by its basis b. This should be the script b, but you get the idea. So here, let's read this note, see what I wrote down here. You've got a vector equation. X is represented in terms of the basis b. You've got the b coordinates. Is equivalent to this change of coordinate matrix. So this is this P sub B right here is called the change of coordinate matrix, which changes from the coordinates. If you multiply the coordinates to this change of coordinate matrix, it takes you back to the original vector, which is this abstract vector. So how do you represent the change of coordinates? Well, it's just the basis vectors slapped down as columns of some matrix is all it is. Yeah. All right. So what do we have here? So here they say if you have a basis for a vector space, then the coordinate mapping from x to the b coordinates is a one-to-one linear transformation. So I'm trying to think if we should go through this proof or if we'll have enough time. Let's just go ahead and get started on it. So let's start with linearity. So we'll let two vectors be inside the domain space for the transformation. And then the codomain is the real numbers. So this transformation T is going from this abstract vector space to Rn, since it has n basis vectors. So now U and V, by the uniqueness representation theorem, have unique weights. So we'll say C1, B1, all the way through Cn, Bn, and V has D1, B1, all the way through Dn, Bn. So that they're unique weights. And we want to show linear. So what that means is that the zero vector is in there. So choosing all weights equal to 0. Zero gives the zero vector in Rn. Then the sum of these two, we want to show that the sum of the weights is the sum of the b coordinates of the weights. Or excuse me, the sum of the vectors is the sum of the b coordinates. So this is really just going to be C1 plus D1 if you regroup B1 all the way through Cn plus Dn for vector Bn. And this right here, if we, let's see, do we want to break that up? So the B coordinates of that, oh, I've done that wrong. So we want t of u plus v is equal to t of u plus t of v. Okay, so what we want to do is the B coordinates of u plus v, so we'll use a script b, is equal to the real vector c1 plus d1 all the way through the weights of cn plus dn, which can be regrouped c1 cn d1 through dn, which gives me the b coordinates of u plus the b coordinates of v. There we go. And then same with a scalar. So we'll put a period here, scalar c, then we'll say c times the u coordinate. Let's do cu in the b coordinates is just going to be c c1 c cn, and then you can pull out that constant c c1 through cn. And then this just gives me c times the b coordinates of u. All right, so this implies that the transformation going from x to b coordinates of x is linear. Can we get one-to-one and onto very quickly and easily? If two things, so to get one-to-one, so we'll just say one-to-one. To get that, so if two things map to the same thing, then we want to say that they're the same thing. So suppose u, the b coordinates of u, equal the b coordinates of v, then that means u equal c1 b1 all the way through cn bn must equal d1 b1 all the way through d and bn, which is v. So they have to be the same because their coordinates are the same. So this right here implies c1 all the way through cn equals d1 all the way through dn. Okay, so that implies one-to-one. And then on to, let's choose a random real vector. So let y be in the real numbers. So real vector of size n. So then y, let's just get a little bit more specific, y1 through yn. Then the b coordinates of, so we could say the b coordinates of a vector. So let's write this out like this: y1 b1 all the way through yn bn in the b coordinates equals y, which implies onto. I did that a little quick. So this last part right here is a little sloppy and quick, but it gets the point across. So I chose a random real vector inside the codomain, and then I showed that, hey, if you choose this random vector, this is inside the domain. If you choose this vector with those weights, then it maps to the random vector that you chose. It's b coordinates. So then that implies onto. That means no matter what y you chose in the codomain, you could find a value in the domain that maps to it. So it's one-to-one and onto. It covers the entire space. So when you have a linear one-to-one and onto transformation, we call that, it's got a special name, we call it an isomorphism, um, which is a strange word, but isomorphism means that the two spaces that you're mapping to behave exactly the same. They are identical with a name change. So maybe I'll write that. So identical spaces up to a name change. Yeah, it means everything about them is the same, just they look different. Yeah, okay, well, let's get to some examples. Consider a basis b1, b2, given here for the real numbers. And suppose x is in there, it has the b coordinates, a negative 2, 3, find x. Okay, so the b coordinates of x are given as negative 2, 3. So that means that x has a negative 2 weight of b1 and a 3 weight of b2. So we can just write it out. Negative 2 plus 3 is 1, and then 0 plus 6 is 6. So there's x. Easy enough. Okay, here's one that's a little harder. It says the entries in vector x are 6, 1 from the previous problem. Are the coordinates relative to this standard basis, e1 and e2, since, so maybe this one's not as difficult, since, so what is the standard basis? E1 equals 1, 0, and E2, so this is the standard basis that we're used to seeing for the real numbers, for R2, and so we would say and x equals 1 E1 plus 6 E2. So you can see that this is just the standard basis. So this right here, we've been using a basis all along. It's almost like it's like, could you learn a new language without knowing a language? And it's like, no, you need a language to learn a new language, right? So it's like here we were using a standard basis to change to this new basis. And then in order to understand what that originally was, we had to go back to a basis that we already understood. So this is the standard basis. This is coming from a new basis, this awkward basis that we don't want to use. All right, let's try example 3. We've got two different basis vectors. X is 4, 5. Here's the basis. They say find the b coordinates. So this is pretty interesting. So what we want is we want c1, b1 plus c2, b2 equal x. This is what we want. So I'm just going to say we want. Well, let's replace everything that we know. We know b, b1. We know b2. And we know x. Hey, this is coming full circle. We've done something like this before. We've been looking for the combination of the two vectors. And so this is really just this matrix, the coefficient matrix, multiplied by c1, c2, to give me 4, 5, which is really just the same as this augmented matrix that we can row reduce. So let's do a couple row reduction steps here. I'm going to swap the two rows. And then I'm going to eliminate this element 0, the 2, by subtracting 2 of the ones from above. So this is going to be a -3 and a negative 9, nope, negative 6. And then we'll divide that bottom row by -3. And then we'll subtract it from the top row. Aha! So this implies that the b coordinates of x in this weird basis is just 3, 2. You can always check your answer. let's just take 3 of B1, 2 B2, and we're going to get 6, 3 plus negative 2, 2 gives me 4, 5, which is x. Sure, let's keep moving. Use coordinate vectors to verify that the polynomials, we've got 3 different polynomials here, P1, P2, and P3, are linearly dependent in P2. So use coordinate vectors to verify that. So let's use a standard basis. So I'm going to say standard basis for P2 is, so here we want 1t and t squared. And so then this is my B1, this is B2, and this is B3. So now we want to write each one of our polynomials, P1, in terms of this standard basis. It's 1B1 and 2P3, or 2B3. P2, so maybe I'll write the B coordinates of this polynomial. So the B coordinates of this polynomial are 1, 0, 2. So now P2, this polynomial, is 4B1 plus B2, and then 5B3. So the B coordinates of P2, just constant is 4, linear term is 1, and then the quadratic term is 5. P3 is just going to be 3B1, 2B2, 0B3. So B coordinates of P3, just 3, 2, 0. Okay, so now we want to see if these are linearly independent or linearly dependent. So let's just use the same method that we've always done to determine if vectors are linearly independent or linearly dependent. So let's put the B coordinates of P1 down in the first column, and the B coordinates of P2 down in the second column, and the B coordinates of P3 in the third column, and then we'll just row reduce. So we'll see if they are linearly independent. So what we've done is we've changed polynomials to real vectors, and then we augmented those real vectors into a single matrix. You could call this coefficient matrix, and then we just want to row reduce. So let's go ahead and start row reduction. So I put equals. We don't want really equals. So this is 1, 4, 3, 0, 1, 2. We'll eliminate that there and subtract 8, so it's a negative 3. And it's going to be a negative 6. And then this last row is just going to be a row of zeros. So the answer is no. They say, are they linearly dependent? The answer is yes. They are linearly dependent polynomials. Okay. Good. Let's keep going. I think I answered everything on that one. Yeah. Okay, next one. Let's see, how are we doing on time? We're doing good. So they say let V1, V2, and X in V1 and V2 form a basis for our space. H is the span of those two. So V1 and V2 is the basis of H. Determine if X is in H. And if it is, find the b coordinates relative to that. Sure, so let's go ahead and just do v1, v2, and x, and see. So what are we doing here when we do that? So when we augment like that, we're really taking c1v1, c2v2, and then we're setting it equal to x. And then we're really just doing v1, v2 as columns of a matrix times the c1, c2 scalars. These are vectors. And then this gives me x. Then we're just augmenting v1, v2 with x and row reducing to find these coefficients, c1 and c2. So 3, 6, 2, negative 1, 0, 1, 3, 12, 7. A lot of textbooks won't even use this vertical bar here. It's not even necessary. The reason that I put it in is just so that we can easily separate the two data points that we've got here. These are the basis vectors. This is the vector in question, whether or not it's in the basis. And so I like to be able to separate our information that way, just to know that this is not one of the basis vectors. Okay, so let's start row reduction. Maybe what we'll do, it's the easiest way to approach this. Let's add row 3 to row 1. We get 5, 0, 10. And then we'll divide row 2 by 6. So that's going to be 1, 0, 2. And then row 3 will stay the same. And then we'll divide the first row by 5. And then we'll eliminate the bottom, the middle row and that 2 there in the first element of the third row. So that's going to be 0, 1, and we had to subtract 2, so it's going to be 3. So let's interpret this here by putting it into a proper form. So reduced row echelon form. This is a 3. So what does this say? It's consistent. So the fact that it's consistent means that there is a solution to that system. And the weights, so the C1, C2 weights, we can go ahead and read them off. They're right here. This column represents C1, this column represents C2, and you can see that we can go ahead and read off those weights, 2, 3. So the answer is yes, x is in H, and x equal 2v1 plus 3v2. All right. So once you've assigned a basis to a vector space, then that automatically brings the idea of a dimension into play, because a basis has a set number of vectors. So here, if you look at the first theorem, if a vector space has a basis with n vectors in it, then any set V containing more than n vectors is automatically linearly dependent. Because remember, the basis is the smallest spanning set. So the basis is linearly independent. And they span V. So if we remove one of these, if we remove linearly independent, it still might span V, but then you no longer have a basis. So if you add on a vector, so if we have, say, n plus 1 vectors, then they no longer will be linearly independent, because you've got too large of a spanning set. You can have a smaller spanning set. This is the smallest set of vectors that does it, which that means that this letter n is somehow unique. So then that's what the next theorem says, is if you have a vector space V with n vectors, then every basis must also have exactly n vectors. So you can have multiple bases. You can have a basis two different bases for the same space, and every basis has to have the same amount of vectors. So this letter n, the number n, I guess, is unique to that space. So that leads us, this theorem leads to this definition. We are safe to define what that number means. So if V is spanned by a finite set, V is said to be finite dimensional, and the dimension of V is said to be the number of vectors in the basis. So that letter, so the number n. And then the zero vector space is just defined to be of zero dimension. So you can technically have a space with just zero. It satisfies all the properties. So we need to, in order for our definition to be consistent, we'll just say that that space is zero dimensional. It has no dimension. So its dimension is zero, is what I should say. So you could say dimension of the space with just the zero vector is just zero. So it's not that it doesn't have a dimension, it's just that its dimension is zero. Okay, if V is not spanned by a finite number, then we say that V is infinite dimensional. We really don't talk about any infinite dimensional spaces in this course. Next one. So let's see here. We've got H is a subspace of some finite dimensional space V. Then any linearly independent set in H can be expanded if necessary to be a basis for H. Also, H is finite dimensional, and the dimension of H must be less than or equal. So this is an actual less than or equal. We're kind of abusing notation here because we've also used this notation, which this is a subspace. So notice the subtle difference between these two. This inequality symbol here is comparing two spaces. It's saying this is a subspace of this space. This inequality symbol is comparing two integer numbers. So the dimension of H is an integer, the dimension of V is an integer. Let V be p-dimensional vector space. P is something bigger than or equal to 1. Any linearly independent set of exactly p elements in V is automatically a basis. So as long as you have that magic number, the dimension, and you're linearly independent, boom, you're automatically a basis. You don't even have to check if they span the space. It's enough. So basically we're crossing spanning off the list and saying as long as you have a linearly independent set within, or P in this case, vectors, it's good enough to be a basis. Any set of exactly P elements that spans is automatically a basis. So that case eliminates linearity. So, so if you know the dimension, then you can basically either check linearly independent or check that it spans. And as long as you check one of those, then it's enough to show that it's a basis. Okay, what's the note down here at the bottom say? It says the dimension of the null space is the number of free variables in this equation. Okay, that's nice to know. And the dimension of the column space is the number of pivots. That's also nice to know. So we're going to probably use that in our notes here. So let's get to it. The dimension of Rn, so dimension of Rn, you might guess, there's n vectors in the basis. Dimension of Pn, you might guess, is n, and you'd be wrong, it's n plus 1. So remember, we just saw the standard basis for polynomials of degree 2. Notice how many basis vectors there are in the basis for the standard basis for Pn. Or P2, there's 3. So Pn is always 1 higher than n, or n plus 1. All right, so let H be the span of these two vectors, v1 and v2. Then H is a plane in R3. Find the dimension. What would you expect the dimension of the plane to be? Well, I mean, I would expect a plane to be two-dimensional, right? But it's living in 3 space. I've been tricked by this before. So let's go ahead and see here. So are these vectors linearly independent? And the answer is yes. So v1 and v2 are linearly independent. And they span. How do I know that they're linearly independent? Well, if I check by doubling v2 to get a 2 in this third position, I don't get a 6 in the second position. So just by simply equating one of the coordinates, if the other coordinates are not equal, then you can tell that the vectors are not multiples of each other. Therefore, they're linearly independent. So v1, v2 are linearly independent and span h. So this implies v1 and v2 form a basis for h, which implies the dimension of h is the number of basis vectors is 2. Yeah, so a plane, rightfully so, is a two-dimensional space. So that would also imply a line is a one-dimensional space. It's a so one-dimensional subspace, I guess you could say. So H is a two-dimensional subspace of R3, which is a three-dimensional space. Oops. Uh-oh. Okay, there we go. Find the dimension of this subspace. So how do we want to do this? Let's go ahead and write... Let's write it like this. Let's write all the coefficients of A in a column. So that's 1, 5, 0, 0. Let's write all the coefficients of B in a column. Negative 3, 0, 1, 0. All the coefficients of C, 6, 0, negative 2, 0. And then all the coefficients of D, which would be 0, 4, negative 1, 0. Negative 1, 5. And then we'll multiply this by A, B, C. And then, of course, A, B, C, and D are all real numbers. Okay, so now let's... where am I going with this? What do we want to do? Let's determine, so I guess we could row reduce that matrix. So row reducing it will still preserve the relationship. So this is just the span. Let's write it like this. It's the span of 1, 5, 0, 0, negative 3, 0, 1, 0, 6, 0, negative 2, 0, and 4, negative 1, 5. Now, now let's check the linear independence. There should be a 0 at the top of this one. So now let's maybe row reduce this. So I'll just row reduce it up here. That's going to be, so 15, and then 30, and then 4. Oh, man. Let me pause the video and continue this so you don't have to go. Okay, so here it is. I started row reducing a little differently. So just make sure it's recording. And so here I started row reducing, eliminated this last, I swapped these two rows and then eliminated this negative 3, and then used that row to eliminate the 5, and then used this 1 to eliminate all the elements above it, and then condensed it to reduced row echelon form. So what this shows me is that this is a free variable. So that corresponds to this vector right here. And so by the spanning set theorem, we can eliminate that vector. So let's go ahead and say that this is equal to the span of 1, 5, 0, 0, negative 3, 0, 1, 0, and we eliminated that one. So this is going to be 0, 4, negative 1, 5. All right, so here, this is a linearly independent spanning set. So this implies that this is a basis. So we'll say is a basis, which implies dimension of H is 3. All right, I think we have one more example here. Yeah, this is the last one. So here they say find the dimension of the null space and column space. So we'll want to use that last note of our examples above. So let me go ahead and row reduce this off camera, and then we'll continue it together. Okay, I've done the row reduction here, and you can see that the pivots right here and here, of which we have 2, those define so this is the number of basic variables, pivot columns. This defines the column dimension of the column space. So pivot columns define dimension of column space. So we can say dimension of column A is 2. And then the number of free variables, here they are. Those correspond to the non-pivot columns. So these are free variables. Define, I'll say number of free variables. And this would be number of pivot columns. Define the dimension of the null space. So in this case, dimension dim. So we just use the Roman letters dim and null. When defining the null of a specific matrix like A, we use 1L. So null A is going to be equal to the number of free variables is 3. And you'll notice here the sum of these two should always equal the total number of columns of A. So you could write columns, number of columns of A equals dimension of col A, the column space, plus dimension of the null space. So in this case, 5. Yeah. All right. So that was pretty quick. Went through it very rapidly. You can pause and speed up and rewind as many times as you need. But I wanted to try to keep it relatively short. Your homework, which is, here it is. I think I pulled it up in a Word document. Is these two. I think I originally, in my notes, or in my original assignment guide, only did one of these sections, but it should be both sections, 4.4 and 4.5. So I am doubling up with some sections here. This one was shorter. I think we were able to fit it in here in a reasonable amount of time. But try to get those two done and uploaded to week 4. So week 4 homework. Week number 4 homework is 4.4 and 4.5 textbook problems. And upload, so we'll say upload to week 4 Google form. And so the due date, what I try to do is I try to enter it in 2 weeks after. So like this is going to be released tomorrow or tonight. So then you have until like Friday the 15th in order to get this done. So by that Friday, the end of the week, is when I will try to upload all of those Google answers. So you basically have 2 weeks to get it done. So I'll just say due Friday, May 15th by 11:59 p.m. And then I'll just update the Google form for the next week. All right, well, thanks for watching, you guys. I'll see you in class.